So we said in the last video that p hat was the point estimate for our population proportion p. So now we want to look at what the confidence interval for that would look like. Now this gray box up here on the top, this is on your gold sheets, your note sheets in the back of the course pack. Those will be given to you on an exam. So none of this gray box here needs to be memorized. You have to understand what it's talking about. So it's saying if you want to build a 1 minus alpha times 100% confidence interval, in other words, your confidence interval for P, the proportion, that's this formula in this box, P hat plus or minus Z alpha over 2, the giant square root times P hat 1 minus P hat over N. Now P hat is the point estimate, which we said at the end of the last video. It's x over n. We learned that formula back in section 8.2, and honestly it's really building on 6.2, which is the binomial distribution, x being the number of successes and n being the number of trials. The critical value is z alpha over 2. And that's what we're going to spend most of this video discussing. So I'll come back to that piece, but let me look at these other portions down here. First of all, we have these requirements that are needed in order to be able to construct this interval. And those requirements should be looking very familiar because they're from the central limit theorem for proportions that we learned in section 8.2. We always need a random sample, otherwise we have bias. We need the sample to be independent. If we're sampling without replacement, we would need little n, our sample size, to be less than 5% of capital N, our population size. And we need the distribution to be normal because that z that we're looking at right there is from the normal distribution. So if you don't have normal, you don't have z. And if you don't have z, you don't have this whole interval. So you need n times p hat times 1 minus p hat to be greater than or equal to 10. And again, all of this is on the notes sheets that you're given on the exam. What isn't on the note sheet is a couple other definitions. That the margin of error is the back half of that interval. So when you look at the formula up here, there's the p hat plus or minus, and then this bit right here from z alpha over 2 onward is called your margin of error. It's the amount you're adding and subtracting away from the p hat, your point estimate, to create your interval. And therefore it becomes half of the interval's width. So if you look at your confidence interval from one end to the other, the margin of error is half of that. From the middle out to the high end, or from the middle out to the low end. The middle being the point estimate at p hat. Sometimes it's actually easier for us, matter of fact a lot of the time, to just use that to find the margin of error. So if I give you the interval already for a problem, if I say the interval is from 10 to 30, then you would tell me the margin of error is 10, because from 10 to 30 is a distance of 20. That means the interval's width is 20, and you would cut that in half and make it 10. Also just notice real quick, we learned this formula in section 8.2 and it's back, that the standard error of p hat is roughly the square root portion of that formula up above, that big square root of p hat times 1 minus p hat over n. Also remember that sometimes we have to use n times p times 1 minus p because we don't have what p was. We learned that in section 8.2 as well. So just a little note that sometimes you have to use p hat instead of p to be able to find those values. And I just highlighted those. This bit right here from the margin of error down would be something that would be very wise to put on your note sheet because they're not given to you in the exam notes packet officially. All right, now we're not actually going to go off and make this confidence interval yet because we know how to find p hat, no problem. We know how to find n, no problem. But we need to talk about this critical value piece a little bit more, because before I go off and do confidence interval after confidence interval, I need to know how to find that very critical component, get it, of the formula. So let's look at what the critical values are. So the critical values, we learned this definition in section 7.2. We learned it for a single tail, and we actually learned both the left and the right, in fact. So z alpha is on the right, negative z alpha is on the left. Alpha, which is your subscript, is the area, right? So the area in the tail is that alpha. For confidence intervals, it's always that the sea level is in the middle, and then due to symmetry, you've got one on the right and one on the left, and the middle part is the confidence interval or confidence level, and then alpha over 2 is one tail and alpha over 2 is the other tail, right? Remembering from chapter, well actually from earlier in this section, that alpha and the sea level are complements of each other. Now you'll notice actually that there's a symmetry going on and zeros in the center. So that means you actually only have to do the work to find one of the numbers. And once you've found the one number, you've actually found the other number as well. All right, now we'll look at how to do this in this problem right here. So we're going to determine the critical values in each of the cases, amongst other things. And we're going to show accurately shaded and labeled graphs, always very important in order to earn the full points, that we shade and appropriately label our graphs, and include our calculator entries and all of that jazz. Okay, so the first part is pretty basic. It's saying find the critical z values corresponding to a 95% confidence. All right, well, I started by drawing the picture, and I put the sea level in the center, just like I should. And then I've got my z alpha over 2, negative z alpha over 2. So all of that is drawn and beautiful. Now remember, alpha and the sea level are complements of each other, right? We've already learned that before. So that means that alpha, since my sea level is 95%, my alpha would be 1 minus 95, which would be 0.05. Now that's the area in both of the tails. But I don't want both of the tails. I want just one of the tails and then the other one. So I'm going to cut it in half. I'm going to take alpha and divide it by 2. That's why it actually says that right in the subscript, z alpha over 2. So you take alpha, you divide it in 2. That will give you 0.025. All right, so then that's what I can go put into inverse norm. I can say inverse norm 0.025, comma 0, comma 1. All right, so I pulled up the calculator here. I'm going to hit second distribution, so second verse, then number 3, inverse norm, and then I'm going to tell it 0.02501. Now, older calculators, you don't have this option of left, center, and right. So older calculators is just automatically left. So you type in 0.02501 left. You'll hit enter or hit paste, and then press enter, and you'll get the same number I've got, which is negative 1.599. In other words, negative 1.960. New calculators like the one I'm working on, you actually have another option. So new calculators, you can hit inverse norm, and you can tell it 0.95, 0 and 1, but then tell it the center. You're saying, hey, the center of my curve is 0.95, and I hit paste, and then hit enter, and it's going to give me both numbers, the negative and the positive, which is what I was about to show you right here. So you get negative 1.960 and positive 1.960, and that gives you both values. Real quick, I'm just going to show you on an older calculator what it looks like. So when I hit inverse norm, see, it doesn't have that left, center, right feature. So for this calculator, you have to use the 0.025. You have no left, center, right, so you just 0.025, comma 0, comma 1, and there it is, negative 1.960, and then you have to know that there's another one that's positive. I mean, you don't have to. If you wanted to, you could find it with inverse norm, but it's not necessary. Because of symmetry, you know, it has to be the same number on both sides. All right, so let's look at the second one. This is the finding the critical values for a confidence level of alpha equals 0.005. Excuse me, not a confidence interval, if alpha equals 0.005, and then it asks what confidence level would use this critical value. All right, so a couple things. One, alpha equals 0.005 is automatically the area in both of my tails. And alpha over 2, equals 0.0025, right? It has to. So then I could find my sea level, right, which is 1 minus alpha, because alpha and the sea level are complements of each other. So I just take 1 minus alpha, that would be 1 minus 0.005, which gets me 0.995, which is that confidence level right there in the center. So I've answered that question. That question I highlighted in green. So the confidence level is 0.995. But they also want to know what those values are. So if I go back to the calculator, I would hit inverse norm. So second distribution, number 3 inverse norm. I would take 0.0025, comma 0, comma 1. I would go down here to paste and press enter. And I would get negative 2.807, which is the one on the left. and then therefore positive 2.807 must be the one on the right because they have to have symmetry. One other comment before I go away from this problem. If you're wondering what 2.5% looks like on a normal curve, this is drawn by computer. This is exactly 2.5%. So that's what it looks like. And then 0.0025 is also drawn by computer. And you can see that when I'm shading a very tiny amount. 0.0025 is very small. So when you're going to draw these pictures and shade them yourselves, you should be shading an appropriate amount. You should not make 0.025 look like it's a huge amount of the tail, because it isn't. But it also is not teeny tiny. 0.0025, however, you should shade as a very teeny tiny portion, because it is. Right? So you should be shading appropriately. You should be labeling everything exactly as I have here. There's nothing on this graph that you cannot write, including the alphas and the over 2s and the z's and all of it. So you have to draw every component here. When you're wondering how would you remember that, put it on your note sheet, right? So draw the pictures that are on this previous page onto your note sheet. In particular for chapter 9 you want the second one, but for chapter 10 you want these other ones. And actually there's one third one that we will show you in chapter 10 as well. So all of this has to be in there, including the symbols and the notation, and you have to shade it appropriately. What I have shaded here is about 2.5%. So that's what it looks like. So be prepared for that. Up here, that's about 5% right there, that alpha. So draw and shade appropriately. It'll be said in the instructions, and I actually mean it. So try to draw mostly accurate and well shaded and well drawn pictures, and make sure you label every component. All right, last problem. So you can see I've already shaded and labeled the components, and it's got the top 6.5%. So you can see I've shaded more in this tail than I did in the other two, because 6.5% in my tail is a lot more than 2.5% or 0.25%, which is what this middle one is. So this is 6.5%, so that's quite a bit. As a matter of fact, again, this is drawn by computer. This is actually exactly what 6.5% looks like. Of course, you're not a computer, so you don't have to be exact about it, but you should roughly know what that looks like. And when you're in doubt, the empirical rule can help you a little bit with that shading. All right, so that's 6.5%. That's the top half. But that means automatically I also have a 6.5% on the bottom half, because together they would make my alpha. Right? So in each of the two tails I have 0.065. So that means that I have 0.13 in both tails put together. So 0.065 and another 0.065 makes 0.13. All right, well 0.13 is the complement of my alpha. So I'm going to take 1 minus 0.13 to get my sea level. 1 minus 0.13 would be 87%. And sure enough, that's my confidence level, 87%, right in the center of my graph. All right, well, great. I've answered the confidence level. Wonderful. They want to know the critical z-value, so technically they want the one over here on the right. This is a little bit of a tricky question because they actually say they want the critical z-value singular as opposed to these other ones which are values plural. So A and B technically wanted both of them. C technically only wants the one that's on the top half, the positive one. That's all right. How do we find it? Well, if we find it with inverse norm, so if I hit second distribution, inverse norm, 0.065, and then go down to 0 and 1 and press paste, enter, I'll have negative 1.514. And that means the positive one is positive 1.514. So the one that they wanted was 1.514. If you're asked to find both of them, then it's plus or minus. Now real quickly, let me go to the other calculator. There, this is the one that has the left center right feature. So if you have a calculator with this feature, you would type 0.87 and leave it in the center. That's one option. And then you would only pick the positive one, say. Or you could do distribution number 3 and say 0.065, but then say it's on the right on a high number, and then press enter. Go down to paste and press enter again. That'll give you the positive 1.514. So there are a couple options with this newer, fancier, schmancier calculator. Oh, and real quickly, if you wanted to do this middle one with this new calculator, I forgot to do that one with the new calculator. You would type 0.995 and then go down here to the center. That's one option. And then paste and press enter. You get the plus or minus 2.807. Or you could put in the 0.0025 and then say left or right. It doesn't actually make any difference. So say 0.0025 and then choose, if I choose the left, it'll give me the one that's on the left. If I choose the right, it'll give me the one that's on the right. So either way would work with the new calculator. So it's just a question of knowing which way you're trying to make this work. There you go.